Yeah, thank you for the invitation and thanks for having me here. So this is also a bit my first talk I give at the university here. So I've taken the idea that I will not focus too much on one very specific topic from a statistical point of view, but talk a bit more about a lot of work I've done over the last years on inferring the spatio-temporal structure of climate variability and its external and internal drivers. So I've worked a lot really on the interface between climate sciences and statistics and working in rather interdisciplinary fields. And so you might see a lot more pictures in this talk than what you usually might be used to, and a few less formulas. But I hope that I can give you a bit of an impression what the statistical problems are that I'm interested in, that I would also be happy to collaborate with some experts on very specific methods in the future. And yeah, let's go ahead. So I've always been interested in climate changes, not just because we currently have rather annoying climate change ongoing, but always found it interesting how we had phases in Earth's history where it was much warmer than we currently have. We just have to go far back enough, something like 60 million years, and then we get to a very hot climate. The last time we had something what we might approach over the next 100, 200 years was something like 5 million years ago, and I always found it fascinating how we can actually do something, graphs like that, how people could know that. This graph is from the IPCC report. From a statistician point of view, it's really annoying. It doesn't have any uncertainty bands, which is stupid because there are lots of uncertainties, and that's also what I'm interested in what are reasonable uncertainties on these bands compared to what we have. We have a very, do we have actually what's the best way? So we only have this very small part here where we actually have quite good instrumental observations where we can actually measure temperature and everything else. Then we want to go into the future, so we use mostly simulators of the Earth system that are producing scenarios of how the climate could be depending on socioeconomic decisions made. And if we want to go further back and understand how climate was tens of thousands of years, hundreds of thousands, millions of years ago, we're working with so-called paleoclimate proxies, which are basically digging into the ground and picking up whatever we have, going into ice or sediments and see what we have there, what might react to or what might have recorded the climate that has been there. More on that later. So looking at all this variability, one question is, okay, on what timescales do we actually have what kind of variability? And the first person who came up with an idea of how this might have looked was Mitchell in 1976. That's why it has this quite interesting graphical properties. So he was thinking about what's actually the spectrum of climate variability, looking at in a spectral space where a lot of climate variability at that time, people were thinking about it's a lot of periodic processes because there's some which we know very well. We have daily variability, we have annual variability, which are the two huge peaks here. At that time, it was just discovered that there were in relatively regular intervals, we had ice ages or glacials, they're called in a more precise way, which have these periodicities of roughly 100,000 years. And so people were very fascinated by periodicities and what might be the drivers of it. And this is not actually based on data for the most part. This is just hand-drawn. So he basically just said, we think we have more or less a white noise background spectrum, and from there we have a lot of periodicities. That's not very satisfying, so people went out, tried to figure out data, and tried to come up with better ways of that. So this is some of the newest versions of this. It looks a bit different. There are not that many periodicities. Sorry, it's not in one part. It's two different ones. The first is going really from the daily part up to 100 to roughly 100 years or a little bit more. And the second one goes from 10 to roughly a million, but more or less, I would say a little over 100,000 is where it afterwards we're not having that much data in it anymore. So what we see, so this is reconstructions, mostly from paleoclimate proxies for the short time scales, it's instrumental observations, and there are also somehow simulators in it. It doesn't actually look that bad in the sense that the simulators we have now are actually reproducing the global mean temperature spectrum, which was also one question. He doesn't really say what spatial scale he's looking at for temperature. And so this is supposed to be global mean temperature, and the models are actually doing a good job at reproducing what we find in the data. So we do have some periodicities left, which are obvious, which is daily cycle and annual cycle. We then have these very long periodicities here on with a peak at 100,000, which is again going to ice ages and back. But everything in between looks a lot more like a continuous spectrum, so which means it's actually probably more climate variability probably is more than just white noise with some periodic processes in it, which also makes it harder to understand because it's much harder to actually figure out what are the processes responsible for having more this continuum of climate variability spectrum. Because we cannot say, okay, we have a periodicity of 400 years, that's definitely solar variations in the solar cycle, which people really love to find in paleoclimate. Usually they're not very robust in their findings. So what's the reason that we actually have all of this variability? On the one hand, we have external forcing, which means we have changes in the boundary conditions of the climate system. We have solar radiation, which is changing on the one hand because of variability in solar activity, on the other hand because Earth's orbit is varying with regular periodicities, and this is mainly responsible for having changes between ice ages and warm periods. We have greenhouse gases, which have usually followed. So, for example, in the last ice age, we had CO2 concentrations of roughly 185 parts per million that went up into the pre-industrial part to around 280, and at the moment we are at something like 410, 420, I don't know, around that. Which, this is the last 100 years, which is not looks a bit different than everything we had over the last 25,000 years before that, and more or less everything else we had over the last few million years. We also have changes in ice sheets and changes in land sea masks. They're quite annoying from a climate perspective because greenhouse gases are relatively easy. They are globally mixed. They change the atmosphere in the same way everywhere on the globe. So they're relatively easy to model their effects. Ice sheets are a lot more annoying because they appear at some place. They suddenly create mountains because it's ice that are a few kilometers high, that is disturbing all the flow in the atmosphere. And the atmosphere reacts quite sensitive to that. And it's a lot harder to sample uncertainty of that variability. There's something like volcanic eruptions that in certain and relatively random time steps perturb our temperatures. We have aerosols and a few other things. We also have internal dynamics. The climate system is a nonlinear chaotic system, and that's why the system would never really reach an equilibrium, but we would always have constant fluctuations from it. And even if we wouldn't have any changes in external forcing. And we also have different components that we have to kind of take together: the atmosphere, the ocean, the land, the biosphere, and the cryosphere. They all have kind of different characteristic timescales, and they interact with each other, and all of that creates variability on different timescales. So when we now think about from understanding past climate to wanting to predict or what's usually called project future climate, what's typically going into these curves in the beginning that I've shown of Earth system simulators, it's kind of a series of models, some of which are kind of related to the applications in the TRR because they're looking also then on impacts on energy systems, for example, or transport networks and their disturbances. But typically we would start with a socioeconomic scenario that basically, I don't know, an economist can maybe explain better than me, but they think about how different broad global decisions would go into how our socioeconomic systems develop. Do they work together? Does everyone work separately? Do we stick with what we do, right? And with all our practices, what we do we want to change things? General questions like that. This then goes into a relatively broad process-based model that tries to connect the human world and the natural world to create curves of future emission scenarios of greenhouse gases and land use, which is then going into so-called global climate models, or what statistician would say it's a global climate simulator, because these are process-based models that you take a boundary, an initial condition, you take in boundary conditions, you have a lot of processes of discretized partial differential equations and other processes in it, and then you produce climate on some grid, which to make that feasible computationally, it's a relatively coarse grid where, for example, the Baltic Sea is basically not visible anymore, and things like that, which might be relevant for European climate. That's why the output of that would then be thrown into a regional climate model, which has a much higher resolution and is better of simulating regional climate change here, which then again would be interesting for what are actually the impact of climate change on our future in Europe in this case, and thinking about how does it change, could it change energy production, how does it change agriculture, how does it change flooding probabilities and stuff like that. So all of these are more or less process-based models. In the end, there's a few more classical statistical models, but so where's actually the statistical point of view? And so some tasks that we can think of more from a statistics point of view, where can we actually contribute? Because from my experience, it's like if you do like a standard statistical model, for the most part, you won't beat a very sophisticated process-based Earth simulator in predicting the weather in the next days or the climate 10, 20,000 years ago or something like that, except for some super new neural networks who start to be better at weather prediction at least. But at the climate point, we're not really there yet. But these simulators have lots and lots of parameters, so statisticians should be involved in developing objective calibration methods for them. And the annoying part is we have to deal with they're super expensive computationally, so it's really quite limited about how many runs you can do, and which means that at the moment most of them do just ad hoc tuning of these parameters and don't really run with a lot of like saying, okay, we would like to have like just a Bayesian optimization of it with lots of runs, train emulators and everything else to do calibration. We also have to think about model selection and averaging. So typically when you see these bands for the future projections, that just means it's a lot of different simulators that all simulate the same thing, and they're all weighted equally in their future, because there's also some politics involved that nobody wants to say my model is bad and therefore it shouldn't go into the projections. But if we actually want to optimize projections, we have to think about selections of different simulator weights and how to deal with dependency structures between them, because they typically share some components while others are independent, and it creates somehow weird dependency structures. We also have bias corrections. Those models are quite good, but they still have a lot of biases. I think we will hear more about that from a weather perspective later on in the talk. So if we do impact assessments, that are also relying on not just the mean climate change, but on actually the distribution of climate in the future. We have to think about correcting biases on the full distribution in the model, whereas at the moment most of the bias correction is just on the mean. And so these are really interesting questions that actually one can do a lot of work on, because many of them for a climate projection perspective, there hasn't been that much done so far. So one part then, now going a bit more into work I've done in the last years, spatio-temporal climate field reconstructions, so which have the goal of saying I want to actually look at climate variability on really long timescales, because if we want to make predictions that are happening on long timescales, we have to also understand if simulators are able to simulate climate variability on long timescales, and ideally also not just global mean variability, but also more regional variability. And if we think about what data we have available for basically reconstructing climate fields, we start with the last decades, where we have satellite data that create enormous amount of data, and it creates, from my perspective, it's a big data problem. Which, what I mean by that is, we are in the process of more or less random deep neural networks that you'll choose for a lot of the statistical problems in there will more or less beat any super sophisticated standard statistical method, and it becomes quite frustrating doing statistics with satellite data. If you go a bit more, where you have instrumental observations but no satellite data, we still have quite a few data where there are problems where neural networks are outperforming more standard statistical methods, but it's not that obvious anymore, so at least there's some work to do. And if you go back more than 200 years, you come to a really sparse data problem, because the data that we dig up in the ground, it's annoying, it's noisy, it's complicated in its structure, and it's quite sparse. And that's where then the statistical fun comes into it. So what I do for that is mostly working with Bayesian hierarchical models. So I want to combine forward models for proxy data, which basically create a model of how what I find in the ground is related to the climate that has been at that time, at that location. I have a process stage which models how we want to interpolate between those noisy observations in space or space and time, and some prior stage with additional model parameters. There are a few different strategies for modeling this process stage. You can more or less go with some kind of Gaussian process modeling. You can integrate physically motivated stochastic processes, which is one of the cool things about the climate system. In principle, we know the baseline physics of it. It's just really hard to take that and just say we know the physics, we can do great predictions purely from the physics, but we can bring some of our knowledge into, for example, this process stage where we can then say, okay, this is the baseline structure that we know from the PDEs of the climate physics, and we can try to integrate that as constraints into our sparse data problem. We also have climate simulators, so we can also use output from there. We just have to check that what we get in the end is not just the product of a simulator, but it's actually reacting to the data. So first problem was a purely spatial reconstruction problem, where I wanted to reconstruct past climate around 6,000 years ago, which was a period where in Europe, at least parts of Europe, it was actually quite warm, a bit warmer than it was during the pre-industrial time, because we had a lot of additional radiation. And so I have fossil pollen as my proxy data that I find. I take a logistic regression model that I train based on modern pollen and modern climate, and I take a spatial structure that is partly coming from simulator output and partly from a Gaussian process that I mix together, and then get these kinds of fields together with uncertainties, because it's a Bayesian hierarchical model, and then I get, for example, here fields of summer temperature and winter temperature, and that gives me these kind of maps. I can also do some cross-validation with it, where I can look, does integrating the data actually into it does help, and for the most part it does. For some data outliers it doesn't. But overall, I get some improvement from mixing the simulators together with my proxy data, and from there, since the TRR is mostly talking about spatio-temporal data, we can go to a spatio-temporal framework. It gets a bit more complicated. We have more stuff there, and so the core here is that I want to have a spatio-temporal climate evolution model that, it's in principle, it's a stochastic processes that takes proxy data, that takes some simulator output at specific time steps, and then in between, trying to find a model that's basically having non-stationary climate shifts in it, and a Gaussian process model for spatial interpolation of innovations, and putting all of that together. So it's mainly 4 different steps involved in it, and so the main part is this climate evolution model, where I'm looking at which is based on a random walk with time varyingly changing step sizes, which are also spatially changing in a simple parameterist way. And then I'm using a Gaussian Markov random field approximation of an anisotropic Matern covariance to model the spatial correlation structures of the innovations. So this is based on the so-called SPDE approach introduced by Lindgren et al., which from a climate perspective, it's a nice approach because it starts with a stochastic partial differential equation where I can find some physics again in it, and that one specifically would just correspond to a Matern covariance matrix, and it's then an approximation because we built a sparse discretization of the precision matrix in it. But yeah, so that was a relatively basic model, but one could think about more complicated stochastic partial differential equations there to put more physics basically into this in the future. So what we then typically do are tests with simulator output. So here, this is a bit of a weird graphic because time goes actually from right to left, because I've often showed this to geoscientists where time goes from right to left because they think if they dig deeper into the ground, then it's earlier, and the top ground is where it is today. What you see is a climate evolution over the last deglaciation, which is a transition from the last ice age into our present warm period. The red one is a simulation I wanted to reconstruct for Eurasia. So this is just looking at the spatial mean over Eurasia, and I did a lot of tests with different noise, different time steps, and did actually do quite well with the general trend. With some of the more abrupt changes, I'm struggling a bit because there isn't that much data that with limited data points to really constrain that, but overall it wasn't too bad in this testing system. I could go into it some more evaluation, but I think I'll skip that for a short outlook. So some connecting that again a bit to the more broader scheme. It's a lot I worked on in the last couple of years was looking at comparing reconstructed and simulated regional climate variability. So I think in the beginning shown this global mean temperature variability curve where simulators are doing a good job. So if we actually go to regional scale, so the global one would be here the left one, it's time series and it's spectral. If we go to a specific location, we have again a simulator in blue, and then we have a reconstruction, and it looks a bit different on the first case. And what we really see in spectral space is that at periods of something like 50 years, they start to really diverge. That's just one location, so that's not very representative. So we dug out and looked at a lot more different locations and put that all together. And then we see that typically somewhere between 10 and 50 years, we start to see that regional variability in models and proxies in these reconstructions is diverging, where we see a lot more regional variability in our data than what simulators would typically represent. So the broad scale methods there was actually what variability on these few hundred year time slices would look like would be more like a 20-year 20-year differences in the simulator than a 400-year in a simulator, which is way too smooth in that sense. We can also go, I did some work on doing that on longer time scale, again, comparing simulators over the last deglaciation with point-weight model data in the probabilistic evaluation framework. I'll jump over that. But the basic pattern was the same. We see a lot more regional variability in our reconstructions than in the simulators. And that's kind of what I'm interested in also from some of my future research, which we've seen that on a point-wise perspective, but we don't actually know how climate fields on these long time scales look like. And I want to work on that by working more on spatio-temporal reconstructions in Bayesian frameworks and developing these spatio-temporal models further to actually reconstruct fields across different timescales. And also ideally leverage this to improve future projections through some of these steps I mentioned initially in terms of inferring spatio-temporal variability, calibrating Earth system simulators, and post-processing projections to better represent the distributions we actually find. And so I'll close just here with some connections of my research, hopefully with some people working in the TRR in terms of statistical methodologies where I'm interested in these different methods and are happy to also discuss more with people working on them from a more methodological point of view than what I mostly do. And also in terms of applications, thinking about how long-term impacts of climate and environmental change influence energy and transport networks, and how we can use post-processed climate fields to consider full distribution of possible climate states if we think about their effects on energy and transport. Thank you.